for me, this lecture and the next lecture are good lectures for a general audience because I feel most of you guys will be interacting. Let's say some of you guys hopefully will be designing chips, I hope, but most of you guys will be interacting with a chip either at the package level. You'll be using it in a printed circuit board. Let's say you're using an FPGA or a microprocessor or an ASIC or something on a printed circuit board. So you'll be dealing with the package, you'll be dealing with supplying maybe building the power supply to the part. I'm worrying about, the clocking. Let's say you want to overclock it or something like that. So all that stuff will be useful, I think, to most of you going into any kind of electronics career. And then the next lecture, which won't be on the test, I'm just going to record it, and it's just for your FYI, for your information. I'm going to be talking about high-speed input-output interfaces to the chip. Again, I think it's an area that if you guys are into microelectronics at all, you will run into, which is these interfaces to the chip. And then also how you actually generate clocks. So these would be like phase lock loops, delay lock loops. These are things that if you are working with FPGAs or a chip, you'll see, and I think it'll be just good to have. So I'll be teaching it at the level of just being able to understand what people mean, or if you're reading some spec on a chip and it says this PLL is doing something, you've heard of the concept and you know roughly what it's doing. Those are pretty complicated topics. Okay, so anyway, let's get started. So today we're going to be talking about these overall big items these are sort of global issues on a chip, which is how it's packaged, how do you distribute the power, and then the power distribution. Okay, so when you get the silicon chip in a wafer, now you'll have a bunch of these chips on the wafer, and you saw it up and all that kind of stuff. You need some way to, almost everybody using the, let me see, did I lose? I still have you guys, I hope. Are you guys all there? Looks like you are.
Yeah, we're still here.
Okay, great. So you need some way to connect up, you need some technique to connect up to these chips. And, these chips need to be, rigid mechanically. Basically, it's like a mechanical and thermal interface to the rest of the system. So let's say if I just look at a chip, let me actually draw it super big. So it'll be, piece of silicon. It's always square because that's how you dice this thing. And, have all, I don't know, billions of transistors in it. And it'll have these things called, you have all of your circuits here, and the stuff's getting distributed in these metal lines, etc. Wherever you had outputs, you have these pads, which are just openings. So a pad might, if I draw a cross section of the pad, let's say this is the silicon. These are, transistors out here. Say that's an NMOS, for example. So N plus, N plus. And so let's say this output goes through, metal 1, we'll go to metal 2, whatever. And then eventually it goes to like the last level of metal, whatever that happens to be. Just draw it in a different color. Okay, so this will be a metal pad that might be, I don't know, 80, 100 microns wide opening. Okay, and then, so these will be all distributed all in the periphery of your chip. And what you'll do, as we'll talk about it in more detail, is you will, epoxy this thing down. So you'll have a package that looks like this thing, and this thing will be like sitting in a cavity inside the package. Okay, and this package will have its own pads. And then there's this thing called a wire bonder. It's a tool that basically you have these really thin metal wires, and it basically touches one side and then touches the other, and basically connects up these really thin, and by thin I mean these might be, I don't know, like maybe 0.5 millimeter wide, like, sort of the width of your hair, aluminum or gold wires that connect the silicon to your package. This package is typically plastic or ceramic. Typically the case, okay? And then inside this plastic package, it's easier to think of it in terms of a plastic. You've got its own connections that come out to what you typically see is a bunch of pins that then go into your printed circuit board, or you'll see ball bonds in the more advanced. You might not see the ball bonds because they're kind of underneath the package, but basically the idea is you are connecting these relatively small 80 to 100. You can't really work with an 80 or 100 micron thing. You're basically electrically connecting those to a pin that you see in your package, like, like sort of an old style package. If you've seen this is what's called a dual inline package. So, it kind of looks like a cockroach. But so basically what you're doing is connecting the stuff on the chip that's all small to a big thing that you can then hold. You can plug it into a printed circuit board hole. You can solder to it. So it's sort of a mechanical, it serves as mechanical because it gives us also some rigidity. So it's a mechanical support for the part. It gives you an electrical connection to the part. After you're done connecting all up, what you do is you seal this thing. So, if you look at like I don't know, like a Intel microprocessor or something, or a Xilinx FPGA, you won't see the chip in the package. Maybe the chip package is that big because it's sealed. They put sort of epoxy on top of the whole thing, so it's protecting it against scratches, protecting it against humidity, any kind of other stuff. So it's also protecting the part. It's giving you a place to, let's say, again, you're talking about a microprocessor that is, it's yanking out, it's got a lot of power consumption, so it would get hot. So it gives you an interface to, I'm trying to do a really bad job of drawing. So I'm sure you guys have seen like the fins on microprocessors or the heat sinks that you can glue onto this package. So it's drawing the heat away from the package. So it's good for heat removal. What else do I want to say about it? So pretty much those are the main functions of a package. It makes the silicon chip sort of usable at the system level, at the printed circuit board level. Okay. Now, one thing I don't think I have anywhere here, just for those of you who are going to get involved with chip design or whatever, for whatever reason, everything inside the chip, all the distances, dimensions inside the chip are all in metric units. Well, I know the reason for that because that's a sensible scientific thing to do. So, you're talking about like some metal line is whatever, 1 micrometers or, something as a millimeter away from something else. Okay. For I don't know what reason, everything at the package level is in English units, at least in the US. For all, I mean, I haven't really worked in any other country outside the US. So, like, if you want to say, oh, how many, what's the distance between these pins or whatever, they're given in inches and this unit that took me a long time to get used to called the mil, which is 1,000th of an inch. So I went through my whole schooling not having heard of mils or anything like that. And, first time I heard it, I thought what they really meant was it was like sort of a misspelling of millimeters or something like that. Totally wrong. It's mils is like just 1,000th of an inch. So 1 mil is 25.4 micrometers. So beware of this. And so everything on the package that you'll see and on printed circuit boards, I don't know if you guys have designed printed circuit boards, but all the design rules are given in mils. Like the metal is like 6 mil wide or something, and the spacing between metal lines is 6 mils, that kind of thing. And for whatever reason, this whole thing starts at the pad on your chip. So when you want to talk about, the separation between one pad to the other one, you start talking about mils. Oh, like this is, 5 mils to the next pad. Don't ask me why, it's really annoying. So just beware that if you are designing chips that it does this switch. Okay, so that's the package.
I've never even heard of mils before.
What's that?
Oh, I just said I've never even heard of mils before.
Yeah, I had not till I graduated from grad school, and I think I was getting some package made in JPL or someplace. I don't remember. And I was like, the worst part about it is I almost got totally screwed because I just assumed it's millimeters, and I wasn't smart enough to like raise my hand and go, "Hey, is this a misspelling or something?" So anyway, that's a good way to go wrong. By the way, have you guys all heard this story? I don't know if like JPL has got a good connection with Cal Poly, but there's this famous Mars mission from the mid-90s.
I think I've heard of that.
Yeah, this thing like slammed into the surface of Mars, apparently. I don't know what mission it was. So, and it turned out that at some point they had mixed up the metric with English unit calculations. And this
they accidentally used imperial units.
Yeah, and just the thing, instead of landing on the surface, is like very infamous. And God knows what the real reason was, but this was what do you call it, the urban myth that it just like slammed onto Mars. So bad. And anyway, I have other stories about this metric in English units going wrong really badly. It does happen, I guess, with mechanical things. So anyway, just beware of that. And again, I almost got screwed, so I just wanted to mention it to you guys. Okay, so that's the point of a package. And there are a bunch of different types of packages, and depends on a bunch of different things. So there are some kind of major forks in the road. You have ceramic and plastic packages. Those are pretty typical. So ceramic so you could make any of these in ceramic or plastic. Ceramic ends up being expensive, but good heat dissipation. And so you'll see it on, say, some like high-end networking chips or sort of a lot of the high-end chips. So you may not, might go through your whole career of using FPGAs and microprocessors and stuff like that. You may never see a ceramic. But let's say if you work in like DoD, some high-end networking chips, some of the image sensors we work with, we use ceramic for other reasons. But that's like, and then plastics is the majority of parts. And the reason it's the majority is because it's inexpensive and it's not as good a heat dissipation, not as good dissipation. It's got a bunch of other issues. The plastic sometimes tends to like flake off, and you won't be like, it's not like stuff that's visible to the, you'd have to look at the part in the microscope. So sometimes some parts, like again in our business, because we make image sensors, if stuff's flaking off the package and dropping on the chip, we don't like it. So that's another reason you might not want to use plastic. But the majority of the parts are plastic. Okay, so that's one big fork in the road. The other fork in the road is through hole versus surface mount. Okay, so again, I don't know how much printed circuit boards you've seen, but if you're going to hand solder something, you want to do a through hole package. And the idea is, if this is your printed circuit board, you want your part to go into it. Let me redraw that in another color. And you want the pins to come through the other side so you can solder through this side, solder the part down if you're doing it by hand. Now, if you've got a sort of what's called reflow soldering or wave soldering in a machine, what you would do is you would want the part, there's no holes, because basically what happens is the molten solder is on the same side as the part. So there you don't want any holes in your printed circuit board, and you do what's called so this is so-called through hole. And that's something like, I'm sure you guys have all seen this kind of stuff in your labs and stuff. So that's an example of a through hole, because the pins are going through the PCB. And this is an example of a surface mount and part, and like, any FPGA almost that you probably used is going to be surface mount. Like the part, the CPU in your PC or laptop or cell phone, it's going to be surface mount. Probably any part in your cell phone, I'm going to guess, is going to be surface mount. So anyway, those are the big differences. Then each one has its own like things that, you have stuff that's, higher pin count, what's called a PGA. I'm just going to, you guys don't have to worry about remembering this, but this is called, PGA stands for pin grid array. It's a through hole high density part, and its corresponding surface mount is called BGA or ball grid array. So, in one case you have an array of two-dimensional array of pins on the bottom of the package. Here you've got an array of solder balls at the bottom of your package, is ball grid array. QFP stands for quad flat pack, and that's kind of like more it's surface mount, but the pins are coming on the side. Okay, so it sort of gets soldered down on the side, so it's lower density than PGA. This is PLCC. So these are all pretty common, so I'm going through them so you guys will recognize this if you ever see it. As plastic, leadless carrier, something like that. Carrier, I don't know if it was that. No. I'm misspelling carrier. No, I'm totally misspelling carrier. Sorry, guys. And this is the, your favorite DIP, which I'm going to guess you guys have all seen, stands for dual inline package. So again, most high-end parts now are surface mount. They'll be Bulgur arrays, and you'll hardly ever see something like DIP. So DIP might be the oldest, and BGA is going to be kind of the newest. Okay. So I talked about, I think I talked about this stuff about how, it has the wire bonds, etc. Okay, so here's another thing that you might run into is something called a flip chip package. So it's, probably mostly, well, I don't know where you might see it. You might see it. I think especially like DoD guys might see it. So what you do is instead of, you could either do this wire bonding approach. So this thing would be sitting in a cavity and wire bonding, like I mentioned. Or, so this is the silicon surface. Or what you could do is you could take the silicon. Let's say you have a bunch of really high density connections on the silicon. And so here, notice that on this case, you're limited to just the periphery of the chip where you can put your connections. Okay. And so, this is all in 2-dimensional, because you got a bunch of crap going on here. And this is area and this is periphery. So you always have less periphery than area, right? I mean, just that's how it goes. So quickly you turn into something called a pad limited chip size. By pad limited, and you'll hear that too if you're designing chips, that means that the number of inputs, output, powers, and grounds you did dictated how big this chip had to be, because you had to fit that all around your periphery, and you can only put them so close to each other. So just because you had that many pads, your chip size grew. Okay, so that's a bad situation, obviously. So what people came up with is this flip chip technology, which is they put ball bonds right onto the silicon chip, and that way, instead of just having pads on the periphery of your chip, you can have, so this is wire bond. So flip chip, you can put these bonds, bump bonds, all over your chip. In fact, you kind of have to, because for mechanical reasons, you got to get kind of a uniform density of these balls all over your chip if you want to use it. And then what you do is you take this and you flip it upside down. So the silicon surface is facing down, and then you solder it down to your package. And then that might have its own balls or whatever to connect up to the printed circuit board. Let me say a couple more things about these things. So when you look at the through hole versus surface mount. Do I want to say this? Wait a minute, let me think about this for a second. No, let's just talk about flip chip versus wire bond here, sorry. So the one problem with, so let's look at the wire bonding, right? The wire bonding, your chip is sitting on the package, so it's making, the whole back of your silicon chip is epoxied down to the cavity of your package. So that means you get a really good thermal, or you can get a really good thermal contact between silicon and package, just because it's sort of area related. But in the case of the flip chip packaging, the two, your silicon and the package, are only making contact where these balls are. So you get less of a thermal contact between your silicon and the package. And as you'll see, what you really want to do is get good thermal contact all the way from silicon through your package, through the air, and removing that air and replacing it with cold air. So you want that resistance to be as low as possible. Okay, so that's a downside of flip chip versus wire bonding. So everything has its own issues. Another thing that this mentions here, another reason to have the flip chip, is one of the big problems on the chip's input outputs is, so as these wire bond inductances. So what you have is, you have, oops, why did I draw it like that? So let's say I'm just going to draw the edge. So let's say this is the edge of your chip, and this is your package. Just looking cross section at the edge. So let's say it's something like this. And here's the pad for your package. And this is the pad for your chip. And let's say this is your, oops. Let's say this is your wire bond, which you plugged in. So like I mentioned, this is like the width of a hair or something like that. I don't know, it might be 200 microns wide. And this distance, you'll actually be able to see this. This distance of this wire bond, this loop, is probably 1 to 5 millimeters. So you'll see, like if you open up a chip, you'll see like these wire bonds all in the periphery of the chip. And the problem is when you have a piece of metal hanging in midair, if you model that electromagnetically, you'll see that it has a lot of inductance. It's going to have a lot of self-inductance. It's going to have a lot of inductive coupling to other metal lines, all the other wire bonds around it. So anyway, the upshot is this will have a lot of inductance. And another rule of thumb to remember, I think regardless of whether you do chipped, well, anyway, so anyway, it's a good rule of thumb to remember. I'm not sure if you're not doing chip designs, if you're doing microelectronics, you need to worry about it, but I think you need to understand this. It's the rule of thumb is 1 millimeter of wire bond is equal to about a nanohenry of inductance. Okay, so anything with a nano doesn't sound too bad, but as you'll see, it can get you into some serious problems. I think I might have asked you guys this before, but have any of you guys worked with, I don't know, like FPGAs or high-speed microprocessors or anything like that, directly connecting up to them?
We had a little bit of FPGA in the Verilog course.
I see. Did you did you actually have any problems with communicating to the FPGA or anything?
I don't think so, because we used like a finished board, so.
Okay.
Yeah, I mean, yeah, when I was using, like I have one just that I use on my own time, but
No.
You have to write like a code to like receive it like bit by bit, and it can be like complicated.
Yeah. So, a lot of times when you're designing your own board, sorry guys, I'm pulling up the water. This kind of stuff ends up giving you a lot of problems, especially on FPGAs and stuff, because you end up having, so imagine if you have, 10 nanohenry, we'll get into that. But if you have 10 nanohenry of inductance that you're trying to get a sharp edge signal through, that can, because a sharp digital edge can have a lot of high frequency components. So this much inductance could give you a lot of problems. Okay. So let me give you guys another rule of thumb. I'm sort of going off the track, but it's sort of on. I want you guys to have heard of this stuff and know these concepts. So So, as you guys know, there's a relationship between time and frequency, right? You have that's the frequency. It's the Fourier transform, right? So you can basically go back and forth between time and frequency. And so let's say you have something with a square wave with a fast rising edge. Okay, so this rising edge, you would do a Fourier transform of this thing, and you end up with a Fourier sequence of sine waves. So you'll end up, I can't draw them, but you end up with a bunch of sine waves. So you'll end up with sequence of sine waves. So this is where like digital and analog start meeting up. So you'll see these fast edges a lot of times on your I/O, right? Like your microprocessor FPGA is pumping out data really fast. So you'll have stuff at let's say like 100 picosecond rise times. Okay, so there's a rule of thumb that I think you guys should remember. I just used it on a talk. That's why it's fresh in my mind. So rule of thumb, that's all there is. So if you take this decomposition of sine waves, so you take your edge, you decompose it in sine waves, it's kind of an infinite series of sine waves that each one of which the amplitude is affecting your rising edge less and less. Okay, it's like less and less of a component of a sine wave. So a rule of thumb of like enough sine waves for you to have a particular rise edge is, so it's the frequency, the top frequency is 0.35. Don't ask me where they got this number, over your rise or fall time, let's say your edge time. So let's say my rising edge is rising edge is 100 picoseconds. So the rule of thumb is the maximum frequency you should worry about is 0.35 over that, or 3.5 gigahertz. Okay, so if you're looking at like a frequency response sort of spec or whatever, you have to worry about frequencies up to 3.5 gigahertz. So when you have a if you guys remember, the impedance of an inductor is J omega L, where this is the what they call radial frequency, I guess. And so as your frequency goes up in an inductor, your resistance or impedance goes up. So basically you end up multiplying this 3.5 gigahertz by your 10 nanohenries. And at those high frequencies, this wire bond will look like a significant resistance. And we'll get to an example of that. So anyway, so the wire bonds tend to be a difficult problem. The other place that the wire bonds, maybe I should just wait. Let me say it now, and then we'll go back to it. Another thing that has a very fast edge, or another thing that has a very fast edge is the current on your power supplies. Let me put it in. So that's one. So like, let's say if you have a bunch of outputs coming out of your chip with your wire bond, and these have, very fast, we're trying to get a lot of data through, and so they have the really fast edges. This is 10 nanohenry. Try not to make those 10 nanohenries, but let's say a nanohenry or something. You end up with like issues here and here. The other place you will get issues is in the power and ground to your chip, because you need to bring power and ground into and out of your chip. So let's look at why that is. So let's say if I look schematically at this, let's say I have a bunch of gates. And remember, we're talking about like millions, billions of gates. And so I'm going to draw one like this, and then the rest of them, I don't know, whatever. Just imagine lots and lots, billions, billions. So they're all hooked up to VDD and all hooked up to ground. Okay. And so the other equation to remember is the voltage across an inductor as a function of time is a function of change in current as a function of time times your inductance. Okay, so what happens, and remember, especially your flip-flops, etc., your clock is getting clocked all the time. So you're clocking hundreds of thousands of gates at the same time in your flip-flops. That means it's like having a current source hooked up to VDD that has, every time there's a clock, you get a sharp. Remember, you only pull, let's say I have a clock. It was every time, what was it? Every time we saw a falling edge, whoops. If you guys remember from the power session, every time we saw a falling edge, we had a current spike on VDD. You guys remember that, kind of? If you, so if this is drawing current, this is clock. So what's going on is every time I see a falling edge, so this is clock, every time I see a falling edge, I'm pulling current out of this to charge up this capacitor. Okay, so I get these huge, and then I have hundreds of thousands or whatever, jillions of these sort of things being clocked exactly on the same edge. That means I got like a really massive change in current, the change in time, because it's a very fast transition. So what happens here? If I have an inductor, so let's say this is the silicon side, this is the package side. What happens is, I'll have VDD here, and every time I get a pulse, I'll get like VDD minus this delta V, which could end up being a big number. It could be like hundreds of millivolts if you're not careful. And as soon as it gets bigger than the noise margin of your logic, or God forbid, like the noise margin of your flip-flop, it's kind of basically you're in deep trouble. So you got to make sure the inductances on your power and ground on basically any kind of high-speed circuits, especially on the power and ground, are much more important than even the high-speed I/O, is low. And a lot of times with chips, if you've got problems with your chip, it ends up being in the power and grounds. And the reason I was mentioning Xilinx is you can, because you have a lot of flexibility in how you align or how you program your Xilinx part. You could, it's sort of notorious, especially like the really high density, big Xilinx parts are kind of notorious for letting you get into trouble with basically having too many edge transitions happening. And if you're as we'll see, you can do stuff to get around this on the board. But anyway, I'm just like that. Those are the reasons your wire bond inductance could be a problem. Okay, so the inductance of the wire bonds is one of the things that we would call the package parasitics. So anytime, this is like, anytime you don't get what you want, that's called a parasitic. This could be a parasitic resistance. It was unintended. It was an artifact. Like any kind of resistance to your metal line is a parasitic resistance. You don't want it. or capacitance or inductance. Those are all parasitics. Or, if you have leakage currents, is sort of parasitic currents. So those are parasitics. So your wire bonds have inductance. They have resistance. You can put capacitors, as we'll see, you can put decoupling capacitors on the package. Those are not perfect. Maybe I should come back to this. But anyway, so you have parasitic inductive coupling. So this is inductive coupling between wire bonds. And this is self-inductance. But by the way, especially on the printed circuit boards now, when you're doing high-speed designs, there are, so this is especially bad news for computer engineering guys, you're going to have to worry about RF and microwave problem a lot more than you would like. Okay, and there's all sorts of ways, because basically that's the kind of problem you're going to have if you're talking about, when you hear some like PCIe or something like that is running at 3 gigahertz or 6 gigahertz or whatever. So this is, you guys, I'm sure you guys are familiar with these interfaces, PCIe or DDR for your memory. These guys run really fast, and these edges means they have really high frequency components, and everything in your packages, in your printed circuit boards, everything turns into really crappy, or if they're not designed well, they turn into crappy transmission lines. And if they're not designed right, they're turned into crappy antennas that are emitting electromagnetic, radiation out into the world. And, this is, you'll like, every time you sell a printed circuit board, sell a module, you have to make sure it's passing sort of the electromagnetic interference standard. So it's not basically destroying everything around it with this electromagnetic noise. So you'll have to, this is why I'm saying it's sort of bad news for computer engineers, because I have a feeling you guys may have not have as much RF circuits and analysis as the electrical engineers. Maybe I'm wrong, but like you'll have to, if you're designing these kind of high performance circuits, you have to start worrying about inductive effects, transmission lines, decoupling, all that kind of stuff. So that's good news is fun. Bad news is you might have to crack the books. Okay. So so that's just some background. We're going to come back to this package parasitics, but basically I think what we're saying here is you have a lot of stuff in the package that you'd rather not have. So that nice electrical interface from the chip to the board isn't just a short. It's going to have inductance, it's going to have resistance, it's going to have capacitance. The different lines are going to talk to each other because of coupling, etc. So the package itself has got a lot of issues. Electrical issues that you have to worry about. If you don't worry about them, you're going to get burned. Okay, so let's now circle back. So that was sort of I dug into a lot of things. But that was just sort of giving you guys an overview. So we're circling back to the first part of this, that is heat dissipation. And this is an example from your book that, I think we talked about this in our very first lecture, but it talks about a 60-watt light bulb having Cm squared. Oh, that's the area. I'm sorry. So it's saying like a light bulb that you touch and it's like too hot to touch has a surface area much, I guess that's what, 30 times? 30x that of a chip, which is Itanium 2. God knows this is so old, like, I don't know, it's like probably 20-year-old chip, 15-year-old chip. So this thing has twice as much power, the silicon chip, over 30 times smaller area. So if you have a hard time touching that 60-watt bulb, you'll have like the chip is going to be like 60 times hotter when you put your finger on it. So the silicon chips burn, like they can get really hot. And most of the time, the real limitation into what you can cram into a chip or how much performance you can get out of it is heat dissipation. And by heat dissipation means like how much heat can you get out of that chip and dumped into the ambient. Okay, so that's the challenge. And most of the time, you have to do that in a cost-effective and area-effective way. For example, I guess you guys may have heard or maybe done it yourself, but you'll hear about like gamers or whatever. They sort of do liquid cooling or immerse their computer in oil or something like that. That's that's examples of like liquid cooling, because those kind of liquids have a lot less thermal resistance than air. Unfortunately, the thermal resistance of air that's just sitting there isn't all that great. So you could get liquid cooling to do a lot better than air, but that's really expensive and it's really hard to do in your cell phone. So you're stuck there. And this next thing is you want to get that air moving. That's why you have like fans in your laptop. But fans can be loud and they're big, so you can't have them in your cell phone. So you basically heat dissipation. One, you got to get the heat out, and two, you got to do it in a cost-effective way. Okay, so heat generation and dissipation are like a serious limitation. Okay, so just as there is electrical resistance, people think of, they do heat calculations using a concept of thermal resistance. This is the only time I've run into thermal resistance. I'm sure mechanical engineers run into it all the time. So this is the equation for the thermal resistance. And just like V, you got V delta V is equal to, IR. Okay, that's for, electrical resistance. What the heck happened to my thing is giving up, my pen. Anyway, so this is, electrical, you have sort of a thermal corresponding thing. So, and for that, you basically have the difference in the temperature. So let's say I have two surfaces, right? You have your chip, and then you have the air, and you have a package, and it's going to have a certain thermal resistance, phi sub j. So this is the thermal resistance. Okay, and P is the power consumption of your chip. So what this equation says, if the air is at, I don't know, what's the air at typically, is at, 30 degrees Celsius, say you're in the lab. Okay, it tells you if your chip is, burning up 10 watts, and the ambient is at 30C, and your package has this thermal resistance, which you can get from your package vendor, what temperature is your chip at? Okay, so this is sort of a simple concept that allows you, you know, the power consumption of the chip, you know, the specifications you have for the ambient, and you know, you can kind of calculate what's the max temperature your chip is at. And remember something, that the higher the temperature of the chip, the, you know, it'll affect your circuits, right? The high temp, if you guys remember, high temperature was equivalent to slow on circuits and leaky off circuits. Both of which are bad. You know, both leakage current would go down, and our on currents would also go down. So like a hot chip is bad. So like typically the max you'd want your chip running in, don't ask me why, is, so max, what they call this, the junction temperature. Man, my pen is giving out. Junction temperature is the temperature at the chip. So this is what you would plug into your SPICE simulator if you want to see how fast your chip is going. So that typically the max is probably 125 C. That's the max I've seen. Maybe some of the really, you know, killer circuits might go to 140. I would bet on it. So 125, and typically for commercial parts, you got to get the ambient at, sorry guys, my pen is running out of juice. Ambient can go as high as 55 degrees C. Okay, so you can have a delta T of whatever the heck that is, 70 degrees. So that'll tell you what kind of package you can have, or it'll tell you what kind of power consumption you can have before you run into trouble. So, and then, you know, the other nice concept with this thermal resistance is, let's say you have, so you have a certain thermal resistance from your chip to your package, back of your package, and let's say you have a bunch of fins in the back of your package. You've got a what is it called? A heat sink, right? And the heat sink has a certain, its own thermal resistance from the package to air. So heat HS. So you can just add those in series, okay? Just like you would if you had two resistors in series. And so now you just add them in series, and then you do the same calculation. So the more thermal resistance you have in series, the worse of a situation you're in. So you want to make sure those are not, you don't have too many too many things between your chip and the outside. But you also want to just make sure that overall thermal resistance is low. I think this is pretty straightforward. It's an example on, again, you've got your package vendor will give you your thermal resistance, or if you're designing, or if you're custom designing a package, you can specify or try to specify thermal resistance. This says, the ambient, again, this must be for a commercial part. So typically, like commercial parts, I don't want to misinform you guys, but so there's a couple of like thermal specs. So you have commercial. I can't remember all the numbers. Okay, there's a certain range. I don't know, let's say 0, take this with a grain of salt, 0 to 70 degrees for the chip package, not the ambient. The problem is these specs are like depending on who you're talking to. If it's a system designer, they talk about the ambient. If you're a chip designer, they'll talk about the package temperature. So this is the chip package temperature. So commercial is 0 to 70, I want to say. I could be wrong about that. And then you've got military. That, I don't know, might be, I really don't know what, or military, industrial. Might be to plus 85 degrees, maybe on the low end, that's minus, say minus 20. I don't know, but it's wider. Typically industrial. That means the chip that you design for military or industrial needs to have tolerance to a wider range of temperatures or higher temperatures. So it'll be more difficult to design. And usually the worst spec is automotive, which automotive just scares everybody to death. And I forgot what the high end is on automotive. So that's the most wide temp spec. So toughest to design typically. So anyway, it says, the temperature of the chip doesn't exceed 100 degrees C, whatever, and then you can see what the maximum power, just with that simple equation. So, okay, so that's thermal resistance. Another thing you'll see a lot is you want to know what the temperature of the chip is. So so this is more from an analog circuit perspective. You have, you can get a ratio of diode currents to basically build a circuit that's so-called PTAT. It's proportional to absolute temp. So basically you can use that as a warning for your outside, hey, you want to check the temperature of the chip, and if it gets too hot, you can turn it off or do stuff like that. So I think it was yesterday, the day before yesterday, I had my cell phone out in the sun and it's like stopped working. I don't know if it probably, it has temperature sensors that says I'm getting too hot, stop it. So that's sort of what temperature sensors, you'll see them a lot in chips. Okay, so that was the thermal effects. So the second thing you have to worry about is power distribution, and the biggest you got a couple of things to worry about in the power distribution. So power distribution just means getting your VDD and ground. If you're just dealing with a digital circuit, you got to get it from the, so let's say I have my part and my package. And the package. And this is VDD on the chip. This is VDD on the package. And then this guy is sitting on your printed circuit board. So this is VDD at the pin. And then you work all the way up to, this is your board like regulator. So this is your VDD coming into your board. Okay, and ideally, you would like this VDD here to be this VDD here. But in reality, you got all sorts of parasitics in between. So as we were talking earlier about the package, you'll have inductances, you'll have capacitances, you'll have resistances, that kind of stuff. So basically what happens is your power supply keeps getting degraded, and of course well, that's not even quite the worst of it. So by the time it gets to your chip, it's already pretty degraded. And then, especially for wire bonds, this is coming to the periphery of the chip, some poor inverter or flip-flop sitting in the center of your chip. You still have to route the power to it, and it's going to have a bunch of noisy neighbors hanging off the same power supply. So like that's going to be like VDD at your sensitive circuit that all of a sudden is not working because you basically lost your noise margin going all the way to it. So you have to worry about all of those things when you're distributing the power. So if you guys remember, I was talking about when you're, a big part of the design of your chip is going to effectively, a big part of the design of the chip is going to just end up the clock distribution network. When you're doing timing analysis, et cetera, that effectively ends up being one of the biggest things you'll do. Just like it burns the most, or one of the biggest power consumption, it also takes up a lot of engineering effort to engineer it. And same thing with the power distribution. It effectively ends up being a big part of your layout, is how to distribute a low resistance, low inductance, lowest area, so most efficient for the particular use, power and ground distribution network. So effectively, that takes most of your engineering time. Again, I think this is, talking about stuff that we already talked about. You have this LDI-DT again for an inductors, delta V is LDI dt, so that's for an inductor, and of course for a resistor, it's IR as the delta V. Okay, and because you have CMOS gates, CMOS flip-flops, and billions of them, your current is gonna be constantly changing on the chip. And depending on what's going on the chip, it might change in a whole lot of different time scales. You'll have your clock going off, maybe every once in a while, you'll go into some mode and you turn on or off some memory bank on chip, and it's going to have a big glitch on your current, or different things could be going on, and you'll see if you if you're ever in back in the lab with an FPGA board, even a simple one, if you actually put a probe, if you got a scope, if you put a probe down on the VDD of just even the package. Remember, by the package is not even the worst of it. The package would be like here. Whoops. It's like here is when you let's say you have your probe sitting here. You'll be like completely horrified. You just won't know why anything works in your chip. Because if this thing is like, if this was a 1.8 volt supposedly chip, put your pin on there, it's not going to look like 1.8 volts. No, it's going to look like some like nightmare. I'm exaggerating here, but like it's going to be, or your ground. It's going to be it's going to look like it's extremely scary. You just won't know why anything works. The only reason anything works on digital chips is because of the noise margins we were talking about. So those are extremely important, because effectively, by the time you're really using these parts in a real system, you're going to have a very, very dirty power supply and a very, very dirty ground. So, okay, what do I want to say? Yeah, more examples. I think it's fairly simple. LDI/dt, another simple example. So basically, you have to worry about both. These are sort of transient. So this is BBB transient, noise on your supply, and this is DC noise, essentially. Okay, so your friend, when you're designing chips or designing printed circuit boards or power supplies generally, how are we doing on time, guys? Sorry, I'm off babbling, but I think this is all going to be important stuff for you guys. What time is it? It's like 6:06. Sorry, I can't see.
8:06.
Oh, 8:06. Sorry, 8:06. Okay, got another 5-6 minutes. So, so what happens? One way to think about it is if, like, let's say you have your packaged part. Now I know what's going on. Okay, got my packaged part, and it's has a bunch of DI/dt going on here. Okay, so this is my package. And so it doesn't have wire bonds, right? The package it's got pins, my printed circuit board, and then I got my regular out here. Or my power supply. Okay, and I got some distance here with a middle line. Whoops, red and green. Okay, so this line has got a bunch of, I don't know, resistance and inductance. So what happens? So every time there's a change in the current, I end up with essentially with having a, depending on if it's the change in current or just a DC current value, I end up having a big impedance here effectively to this point. So I'll lose a bunch of my power supply. Okay, so what does a decoupling cap do? Well, the decoupling cap, I don't know if you guys have seen it in the lab or whatever. Let's say I put a capacitor here that looks like a surface mount capacitor. So this is a capacitor. So what that really looks like, so if you look at, if you look at a typical board or any board really, you'll see what looks like a bunch of little, they're usually, depending on the value of the capacitor, they might be anywhere from, typically 100 nanofarads all the way up to 47 microfarads, these kind of values. The bigger the value, physically the bigger it is. So I don't know, like a 47 mic might be 2 or 3 millimeters on a side. 100 nanofarad might be, how big is it? It was like less than a millimeter on a side. Okay, so you see these sprinkled all over the board. And so what they are is they're really charge reservoirs. So what they do is they have a certain amount of charge that they're holding. Okay, and if you get a momentary surge in current, these capacitors can supply that current. They'll start going down in value, have to like dump charge back in there. But just for that moment that like you have this big charge of this big surge of charge, they can locally provide that current with low inductance because they're sitting right next to your package. So they have a lot less inductance than stuff that's further away. So the location of these decoupling capacitors, the physical location matters a lot. You want it to be really close to the part that they're decoupling. Okay, so and then depending on the temptation as well, I can use all of it. The bigger the capacitor, the the bigger the charge reservoir, so I can use the biggest value capacitor that I can fit into everything. The problem is these capacitors themselves, again, they look like, I don't know, little things like that. I'm sure you guys have seen them. Maybe you didn't recognize what they are, but they also have their own, because they're actual physical parts, they have their own inductance, own resistance, etc. And it turns out the bigger the cap, it's physically larger, so means the bigger its parasitics, especially inductance. So what you'll see is, if you look at the impedance of a capacitor with frequency, you'll see like where the capacitance is kicked in, and this is where either the resistance or the inductance have kicked in. So it's only sort of good at a certain frequency range, a certain capacitance. So what you do is you use multiple capacitors. So for low frequency, you use 47 microfarads or 10 microfarads. And say so that this would be for this one. For here, you would use, say, 1 microfarad, typical, or 0.1 microfarad. And then for this one, use, I don't know, 100, like that's the same as a 0.1 microfarad. So that one is 0.1. So what you do is you put all these guys in parallel with your supply. So VDD. Or 1 or whatever, to sort of you're trying to get a flat, low impedance supply. You won't be able to get it because we don't have a continuum of capacitors, but that's what you try to do. So what you also see on a lot of boards is a bunch of different size capacitors. And usually they're either you're putting them on places where there's not a lot of, the frequency response, or they'll be working in parallel. So a bunch of them are hooked up together. Boy, we're running out of time. So anyway, what you'll see is, so because they're providing this surges of current, you'll see, and because the processors or the chips, there's like different things happening at different times. Depending on the frequency of impedance, you'll see the different aspects of your board, your package at different frequencies, giving you problems, and you have to put like decoupling capacitors, etc., over there. So unfortunately, I'll have to stop here. I think we're running out of time tonight. So what I'll do is I am not going to put any of this stuff on the test, but I'll record the rest of the stuff on clock distribution, which I think is pretty interesting. And then on the IO and, PLL, DLLs and stuff, because I think those are all kind of good stuff for you guys to know. And, if you get a chance, you can watch them. And if not, it won't be on the test. Okay, guys, so I'm going to stop here.
So when is the test?
The test is on Tuesday. The starts at the normal class time, and you'll have like 24 hours to turn it in again.
Okay.
Okay. Oh, and then this reminds me, I'll put this up on also. So the project is due on Sunday, the 13th. And at least one of you guys asked for a extra credit. So I'm going to put a simple to describe it, but somewhat difficult to do third project on the announcements tomorrow. So to give you a hint, it'll be to design a flip-flop and tell me the setup and hold times, but I'll describe it in a little bit more detail. And that would also be due on December 13th.
Professor, if you have a quick chance, can you like look at the project 2 first problem? They give us like a spice deck for the capacitance, and I was kind of confused on how to like implement that spice deck in PSpice or LT Spice.
On project 2, they give you a, sorry, can you say that again?
It was a spice deck for extracting effective capacitance. It was for the first problem. Like, it was
Oh,
just
yeah,
like this,
yeah.
like,
Right. Sorry, I'm like completely on space. So can you ask the question again?
Yeah, I was just having issues because I made a spice directive in LT Spice and it wasn't like reading it properly. So I was wondering if there was another way to go about that. Because I'm not too familiar with LT Spice. I don't know how to like implement the spice deck.
Gotcha. Can you email me your LT Spice stack and just put in your email, put in like what issues you're having?
For sure. Yeah.
Okay, appreciate it.
Thank you.
Thanks.
Professor, have you uploaded all the recent lectures?
I'm pretty sure I have. Is there something missing in particular?
Oh, I was just wondering, and
Yeah,
the one
I
from this week.
Yeah, this week, sorry, I didn't get, I totally screwed up. I didn't get a chance to do it yesterday. So I'm going to do it, instead of it, I'm going to do the add-on that won't be on the test tomorrow or Saturday.
Thank you.
Sure. Anything else, guys?
Thank you. Bye, Professor.
Okay, if not, yeah, have a good luck on all your finals and the project. And if I don't talk to you guys, have a great and safe Christmas. Take care. Or holidays.
You
I
too,
should.
Professor. Thank you.
Thanks.
Merry Christmas.
Have a good one.
Goodbye.
Bye.
Take care, Professor.
You too. Bye.